Okay guys, so in this video we're going to talk about 7.7, which is the approximate integration using Simpson's rule. There's actually multiple ways to approximate integration. You've actually done them already in Calc 1 using left and right hand bounded um, uh, like sums, right? Your left hand sum, right hand sum. You may have done like the average of those two, which is actually a like midpoint sum. So if you were thinking back to finding some curve, right, basically you would break it into some intervals, and these intervals would be delta x wide, if you recall, and they're always that same width. Now there's actually methods as well that when it's a nice simple shape, they do like a nice constant width. But then when it's a more complex shape, they make those intervals tighter so they can be more accurate then. But like I said, there's actually a lot of integration approximations, but you may remember this. We had something, and a left-hand sum started at the left-hand portion and kind of just drew a straight line over, found the area of this, and then found the area of that. When you did a right hand sum, it was just the opposite. You started on the right hand of each and drew a rectangle. Okay, and then you actually had a midpoint one as well, you may or may not have learned, where basically we go off the center of that delta x right here and we draw a line either way and do the area. And that functionally just approximated, it just took the left and right hand sums and took the average of them, which is a more accurate depiction. So those were some of those ways, but there's actually quite a few ways, as mentioned. One of those ways is called the trapezoid rule, where you kind of do like the left-hand rule or right-hand rule, but then you draw a triangle up to that next point. So you create a trapezoid and find the area of this triangle and find the area of this rectangle, and it's a better approximation. But to be honest, the only one that you really need to know for this class is going to be Simpson's rule. Personally, I mean, it is a pretty accurate way to approximate, and it's pretty easy to do by hand, so that's kind of its value. We have more accurate means in a modern world, obviously, with technology to approximate things to the point where it's basically the same. And so Simpson's rule is maybe a little overlooked because of that. But in this class, it's actually the only one you need to know, and it's kind of important for you to know, at least here at Pima. Okay, so let's talk about what this does. So basically, instead of using like straight lines and stuff, Simpson's rule uses parabolas to approximate a curve. So it basically draws parabolas here between these curves to try and approximate the area. So the blue is the parabolas that are being drawn, and the red is the original function. So if you notice, I mean, if you're trying to fit a curve to a curve, one, that's kind of a challenge conceptually, but a curve is definitely a better depiction of a curve than, say, a straight line. So it kind of makes sense to use this, but like I said, it's pretty much the only one we really need to know for this class, and it's pretty easy. It follows a formula. We'll talk about that in a sec. The one thing to note is that we look at an even number of intervals, so it requires this even number of intervals. And you might say, okay, well, here's 1, 2, 3. Why are we saying an even number of intervals when we're clearly have 3 regions here? Well, first of all, it's actually x sub 1, so we have this region here, 6. Okay, 1, 2, 3, 4, 5, 6 regions here. Now, the number of points you'll have though will be odd. So if you look here, x sub 1, that's 1, 2, 3, 4, 5, 6, 7. So you might say, ooh, that's not enough. That's not right. Okay. Well, 7 points are required to get 6 regions. Okay. So, or 6 intervals. So that's something to be aware of, is that you sometimes, I'm not going to pull a trick on you where I give you, oh, use Simpson's rule, and then I tell you to use some, incorrect number of intervals or something like that. That's not a trick I pull, but it's something to note, is that we need an even number of intervals, which comes from an odd number of points. Okay, so here's the formula. The integral from a to b of f of x dx can be approximated using Simpson's rule, which is approximately equal to the Simpson's rule again. Delta x, again, what is delta x? If you recall from Calc 1, delta x is your b minus a over n, right? So you're like first interval, your last point, your first point, and you divide by the number of them to find that size. Again, I think in general, this right here is delta x, this right here is delta x, this right here is delta x, and so on and so forth. But that may be beneficial to remember that as well. But basically, we take this delta x and divide it by 3, okay? And then we take the first y value, so our initial point, x sub naught. Then we say plus 4 times the second one, plus 2 times the third one, plus 4 times the fourth one, plus 2 times the etc. So it goes basically original 4, 2, 4, 2, 4, 2, 4, 2, 4, 2, 4, 2, 4, 2, until we get to the end, and it's always a 4. So we'll go 2, 4, then it will go to the last value, and it's just a 1 again. So that's it. That's all we're going to be doing. Pretty straightforward. It's just a matter of knowing the formula. I'm not going to make you memorize that formula, but it's a pretty straightforward one anyway. Let's take a look at this thing. So we'll go ahead and snip it, just at least for our initial one. Oops. Okay. All right, so use Simpson's rule to approximate the given interval from 0 to 1 of the square root of 1 plus x cubed dx. Now, the reason we're doing this, I mean, this is actually a really good example of a situation where when we have square roots are often problematic for our integration. And so the reason why we're actually learning Simpson's rule is because we're going to talk about some things that use a lot of square root integrals. And if we can't find an integral, then we can at least approximate it. So we're going to talk about that with this. Okay, so again, we have our formula. It's here. So basically what we're doing is we want our n to be 4. Okay, we're doing it from 0 to 1. So if you think about this, from 0 to 1, n is 4. Let's go ahead and graph it, actually. That would probably be a better way to visualize it. So we have the square root, but f of x is equal to brackets from 0 less than or equal to x less than or equal to 1 of our square root 1 plus x cubed. Okay, so we're looking at this region. And basically what we want to do is separate this into 4 regions. So what's our delta x? Well, you can find delta x using that formula if you want. I mean, it's not that hard to do, but our delta x here is going to be b minus a, so 1 minus 0 over 4, which is 1/4. But I think that would have been obvious anyway here. So basically, our first point is x is 0. Our next point, x is 1/4, and so on and so forth. In fact, I think a table would be a better way to describe it. So let's create a table. We have x and f of x. So we have x is 0, 1/4, 1/2, 3/4, 1. So it's these points here. Okay. So what we're going to do then is we are simply going to plug these y values into our function. So essentially what this is saying is this integral is approximately equal to delta x. Again, delta x is 1/4, how wide our intervals are, divided by 3, times f of 0. Well, f of x sub naught, which is 0. So f of 0, if we plug 0 in, we get the square root of 1. Okay, again, right there. Plus 4 times f of x sub 1. That's our next value. So our next value here is 1/4. So it's basically this square root of 1 plus 1/4 to the third power. Plus 2 times the square root of 1 plus our next value, which is 1/2 to the third. Plus, now we go back to 4. So it always goes original, 4, 2, 4, square root 1 plus 3/4 cubed. Plus, then our last one, Our last value here is just the regular, so square root of 1 plus r1 cubed. All right, so that is our area. So we'll go ahead and plug that into our calculator. So 1/4 divided by 3 is like saying times 1/3. So that's going to be 1/12 times, we have 1 plus 4 times the square root of 1. I know that I have these and I could pull these, but they're approximations. I might as well take as good as I can do. 1/4 to the third plus 2 times the square root of 1 plus 1/2 square cubed plus 4. You have to be real careful typing in a big mess like this. I'm not going to do anything to you where I'm doing like 1,000,000 to you on a test or something. I'm not that cruel. 1 plus 3/4 to the third plus the square root of 1 plus 1, which is 2. Okay, we get this. So our integral is approximately equal to 1.11136323226. I'm just going to pull it all the way out here. Okay, now, how do we know that that's, a decent approximation? Well, let's go ahead and take a look at Wolfram alpha real fast and see. So if we take the definite integral from 0 to 1 of the square root, actually I can use that, I'm not used to their updates here, 1 plus x to the third dx. Okay. And we can find this integral, which is 1.11145.111. I mean, that's pretty darn good, especially when you consider the fact that we are only using 4 intervals. I mean, that is pretty darn close, and that goes to show that Simpson's rule is actually pretty darn good for such a simple function. Like, it's a really simple thing, and it actually works quite well. All right, let's do another one. So now we're going to use Simpson's rule to approximate the given integral of e to the x plus cosine x dx from -1 to 2, and is 6. Okay, so this is a little bit more challenging, I guess, of a function, but nothing too bad. I'm going to just take my function. This is from -1 until 2, and I'm going to change this function to be this new one, e to the x plus, I need a parentheses, x plus cosine x. Okay. So we're looking at this thing here, and we're actually changing this. So our n is 6. So again, if n is 6, delta x is going to be our 2 minus -1 over 6, which is 3 over 6, which is 1/2. So delta x is 1/2. So that is to say, I'm going to get rid of these. All right. So our first value is -1. Our next value is going to be -1/2. 0, 1/2, 1, 1.5, 2. So we get that 1, 2, 3, 4, 5, 6, 7 here. Again, 7 points to get 6 intervals. Now, one thing to note about this is that we actually use all the points. If you recall from left and right hand sums, the left hand sum doesn't use the last value, and the right hand sum doesn't use the first value. And so, how accurate can a model be if it's actually not even taking into account one of those values? So another benefit of Simpson's rule is it actually takes into account every point, or at least every point that we care about taking as accurate as we want. Okay, so it takes the beginning and the end. So that's another reason why it's more accurate. But also, fitting a curve to a curve is often a more accurate way to do it. Okay, so we have these values, and again, it's the same thing. We have this integral is approximated by 1 over 2 divided by 3. It's always divided by 3 times our f of our first point. So I'm going to actually use these numbers here. I don't have them selected correctly. 1, 2, 3, 4, 5. Okay, now I have them. So I'm just going to take their approximations here. These things. Fine, whatever. Okay, so we are going to have our first value, which again is this 0.631. I decided to do the shorter one because I'm lazy. Plus 4 times 1.459 plus 2 times 2.718 plus 4 times 3.965. I'm running out of room. Plus 2 times 4.666 plus 4 times, um, 4.81 plus just the normal 4.874. Okay, so 1/2 divided by 1/3 is going to be 1/6 times our 0.631 plus 4 times our 1.459 plus 2 times 2.718 plus 4 times 3.565. That's 965, excuse me. When I start writing smaller, it gets even worse. My handwriting's even worse then. Plus 2 times 4.666 plus 4 times our 4.81 plus our last value, which is just 4.874. We get 10.205, and again, I cut those off at just 3 digits and didn't go here or a more exact approach, but you know, whatever. It's an approximation, right? Let's go ahead and see what Wolfram Alpha says is this actual integral from -1 to 2. Now, another thing to note is, just like in the previous one, the reason why we're approximating this is I haven't a clue how to integrate this thing. Like, if you have some suggestions, feel free to let me know, but I don't know how to integrate this thing. So let's take a look. So approximation is the only thing I really have working for me. Now, even by cutting it off, like I did, we got an approximation of 10.200, and that's, I mean, really, if you round this, 10.201, 10.202, I guess, or whatever, but I mean, that's pretty darn close. So in science, if you think about it, right, we know from like chemistry or physics, we have your like significant figures. So think of how many times your significant figures honestly go past a few digits. Like, realistically speaking, this is perfectly exact for us. This is as exact as we really need them to be oftentimes. And again, we're not even taking this very far. Like n is 6, that's not very many. Anyway, so that is our Simpson's rule. And again, Simpson's rule is an accurate way to approximate things. It's not like insanely accurate, but it's pretty darn good. And in many cases, it's good enough for many applications in the real world, honestly. I mean, when you are in, I know that many students taking this are engineering students, and so oftentimes engineering is pretty approximate as well. I mean, if you think like floodplain models and stuff, those are like hugely approximations. And then considering the fact of how many engineers use like pi to describe, or use 3 to describe pi, I mean, they're already approximating like crazy. Simpson's rule would probably do the job very well for them. Anyway, thanks for watching.